Hi, my name's Tim Germann. I'm a scientist at Los Alamos National Laboratory. I also lead the Codesign portfolio within ECP, and I'd like to describe a bit of that to you today. Your first question might be, what is Codesign and what's its role within ECP? Just in the 21st century, we've seen an incredible growth in computer technologies. Most people today carry around a cell phone in their pocket that's far more powerful than the fastest supercomputer in the world was back when I was using it in graduate school. In order to highlight science and engineering simulation requirements, constraints, and use cases within this much broader ecosystem, DOE established 3 application co-design centers a decade ago. These were charged with identifying and evaluating trade-offs between application codes, system software, including programming models, and architectures. As it turned out, the growth in these 3 areas was so rapid and the design space so complex that the tightest co-design was really at the software middle layer. So when ECP was set up a few years later, it was organized into 3 focus areas: hardware and integration, software technologies, and application development, with co-design spread across all 3, but particularly within the co-design centers at this middle layer. So there are 6 such co-design centers. Each is focused on a different computational pattern or motif. When you want to model a chunk of material, say a turbine blade in a jet engine, you need to somehow translate that material behavior into a set of mathematical equations that the computer can solve. 2 common ways to do that are either to overlay an imaginary grid or a mesh over that material and represent it as a bunch of small blocks, say cubes that are a millimeter on each side. Or you can model the material as made up of a bunch of particles, even all the way down to the individual atoms that make up the material. 3 of the co-design centers are focused on these traditional mesh and particle methods. The other 3 are more data science oriented, including machine learning and graph analytics. To give you an example, the AMRX Center shows how such an abstraction, in this case, a mesh that has different resolutions to capture different length scales that might be involved, could be used. 6 ECP applications, shown at the top, as well as several others outside ECP, build their application codes using the AMRX library. And just since the start of ECP, this has given immense benefits, since the first 2 exascale platforms, Frontier and Aurora, derive most of their computational power from graphical processing units, GPUs that have been developed by AMD and Intel respectively. To most effectively use these GPUs, at least in the short term, you need to write programs that use a low-level programming model that's closest to the architecture. It's called HIP for AMD, DPC++ for Intel, and they're both different from the CUDA model that NVIDIA developed for its GPUs, which are in the current leadership machines. So instead of these 6 application projects and others outside ECP having to rewrite their code for each of these new architectures, they can all immediately run using the AMRX library. A second example is from the COPA Particle Center. In this case, the Cabana particle library, which was conceived, designed, and developed as part of ECP, provides a similar portability layer. The XGC particle in cell code, which is used to model fusion reactors, was actually 3 different codes just a few years ago. 1 for traditional processors or CPUs, 1 for many-core processors, and 1 for GPUs, in particular NVIDIA GPUs using CUDA, as I just mentioned. The plots here show the relative time that a simulation takes on the Cori and Summit supercomputers, which are based on these many-core and GPU processors, respectively. In each case, the version of the code that was customized for that architecture outperforms the general CPU code, as you'd expect, and by almost a factor of 15 for Summit. The surprising result was when they rewrote just some key portions of their code to use the Cabana library. This single new code version outperformed both of the specialized codes for both Cori and Summit. So now they just have 1 code to maintain and not worry about keeping 3 different versions consistent. And it's actually even better than that, since when new architectures came along, as mentioned, the new AMD and Intel GPUs, as well as the ARM-based processors in the Fugaku supercomputer in Japan, the XGC team could immediately use their single Cabana-based code instead of having to write 3 new versions for these 3 different architectures. So I hope this has given you some sense of the power and utility of co-design centers within ECP and more broadly.